All right, audio and video is up, slides are up, we are live. Welcome back to Statics. We are on lecture 21, which I think is a fairly reasonable way to state we are right in the middle of the semester. Couple quick announcements. So homework 4.1 was due today. Homework 4.2 is assigned today, and I want to talk a little bit about schedule because we have an exam coming up. Our exam 2 is going to be next week. It's going to be next Wednesday, and we're going to do the same thing that we did in the last exam. So Monday we're going to have an exam review, and then Wednesday we're going to have our exam. I don't know why that doesn't have a space there. I don't know. I'll fix that. One thing I'll say, the exam is going to be of the same format and the same logistical delivery. So, you know, how we did the timed exam and then the work upload, all of that is the same. So nothing will change there. The focus of the exam, I guess the best way of saying it is if exam 1 was all about forces, then exam 2 is all about moments. So exam 2 will be everything from when we started cross products up until essentially the topics that we're covering now, which is rigid body equilibrium. What we're going to do today is today is actually probably going to be pretty short. It's not going to be a very long lecture. We might even end maybe even like by 12 or 1:30, because all we're going to do today is focus on fixed supports. See, everything that we did Monday was on simple supports. The structures that we analyzed were pinned or rollers, and so today we're going to do a fixed support. And then if you look at this chapter of the book, is probably the one that's the most sparse because there's not really a lot to it per se. If you understand how to compute forces and how to compute moments, this is just sort of the tying everything together chapter. Is the best way of saying it. Like if you go back to what we discussed last time, so this was this was basically our discussion with rigid body equilibrium, is that if you have a system, a rigid body, not a statics of particle system, I should say, but if you have a system that's in equilibrium, then the sum of the forces equals 0 as well as the sum of the moments. And so in 3 dimensions, that means you're dealing with equations, and in 2 dimensions, you're only dealing with 3 equations. Probably what we'll do is Wednesday we'll look at 3D systems. Friday I'm sort of tossing around what I want to do Friday. I'm not going to assign a homework on Friday, so it may be just me demonstrating some additional stuff with 3D, and I may try and dip into our next topic, the one after the exam. I haven't quite made up my mind how I want to do that, but I can tell you that rigid body equilibrium in 3 dimensions, if on the exam, will be fairly basic. Not because I'm trying to make it easier on you, but if you understand how to do 2-dimensional equilibrium, 3D is just more. The way I look at it, it's not harder, it's just more. But what I think is important is that you understand the different types of boundary conditions that you can deal with. And so really, you know, the way that I sort of break this up is in 2 components. We're either dealing with simple supports that have unknown forces at the support, or fixed conditions that have unknown forces and moments. And so what I want to do today is I really just want to focus on this example. This example is we have a frame that has a series of loads on it as well as a fixed support. If you look at support C is a fixed support, so it's going to have 3 unknown reactions. It's going to have an unknown reaction in the X direction, an unknown reaction in the Y direction, and an unknown moment reaction. And so we're going to need to determine all 3. And what we're going to find is that it's actually a pretty straightforward problem. It's pretty simple. It's just I want to make sure that you don't forget what's going on. But I also want to make sure that everybody here has sort of a physical understanding of what's going on. So let me stop the share. I want to show you this. So this is my little rubber beam mock-up that I use in a lot of my classes just to demonstrate what's going on. And what we're looking at today is an example of a fixed support. And so the easiest way of describing a fixed support is, you know, with an object like this, if you're holding it in one hand like this and you apply a load to it, you can use maybe your pencil or something while you're watching the video. Like imagine if you had your pencil and you hold it really, really tight on one end and sort of do that. And if you do that, you can sort of feel your fingers on this end sort of wanting to rotate the pen back, right? You're trying, this finger, the one that you're loading the pen with, or loading the beam with, maybe I should say, is, it's wanting to rotate the beam, and so your fingers are kind of wanting to kick it back the other way. What's happening from a static perspective is that if you have an element and you subject it to a load, like this, well, not only is this load wanting to translate the body up and down, but it's also wanting to rotate it. So my hand that's holding the beam up is not only having to keep it upright, but it's also having to keep it level. So my hand's actually sort of doing two things. I'm holding it up and I'm preventing it from rotating. And so at my hand, whenever I load this beam, this hand is resisting not just an upward force, but a bending moment as well. My hand is having to twist it in the other direction in order to keep it flat. And so today what we want to do is we want to look at how to compute those. And again, like I said, this is probably going to be a pretty short lecture. Like I said, we might get done 1:30 or so, and that's fine. I always said that each day would be on a given topic, and if we end the topic, we'll end the lecture. So today might be a short one. Let me pull my screen share up. Okay, so here's the problem that we're looking at, and so to be clear, the goal of this problem is to find the reactions. Let me move my keyboard here out of the way. The goal here is to find the reactions, and so what I mean by that is at point C right here, there's going to be three unknown reactions, and so we'll write it as a reaction here. We'll call this maybe CX. A reaction here, maybe we'll call that CY, and then a moment reaction. There's going to be a moment reaction here as well, and maybe we'll write it like this. And you could call this however you want. Sometimes I usually end up just calling it something like MC. Now notice the way that I've drawn these. I've drawn them according to the positive sign convention that we've accepted up until now, that all forces to the right are positive, all forces to the up are positive, and all moments that are counterclockwise are positive. Again, it doesn't really matter what direction that you assume things at the beginning, as long as you maintain a consistent direction throughout your calculations, and that when you express your answer at the end, that you've taken into account any issue with sign. Now, before we start breaking this problem down, I want to recall. If you look at the problem statement says, knowing that the tension in the wire is 1,300 newtons, determine the reactions. So maybe what I'll say is recall the tension in the wire is 1,300 newtons. And I think that's enough to go ahead and get this figured out. Okay. Now, before we start, applying our equations of equilibrium, the first thing that I kind of want to do is I want to look at this. I want to look at this wire. Okay. So let's look at this for a second. So first off, let's do some geometry here. Okay. So let's look at maybe geometry of the wire. And there's a couple of ways to look at that. Maybe what I'll do is, just in the interest of tying this to topics that we've done in the past, maybe I'll try and be pretty formal about it. So what I want to do is I want to look at essentially this triangle. And so what we'll say is that this is point D, this is point B. So what I'm doing is I'm basically taking like this triangle over here, and I'm sort of seeing if I can express this this geometry here. Now, just to make sure everybody's paying attention, what is that? Or I was about to say, what is that? And then I told you. Man, my coffee hasn't kicked in. I think that's the issue. Let me move this down a bit. Okay, let's try that. Let's try it again. All right, somebody help me out. What is this dimension? Okay, there we go. All right, all right. I shouldn't have done the other one, but I just was drawn away, and I just, oh, it's 250, and didn't even think to write. Okay, all right. So this triangle BD has a height of 600 millimeters and a base width of 250 millimeters. So help me out. What is the length of the hypotenuse? Let's see if everybody's paying attention this this Monday afternoon. How would we do that? I see somebody said 650, and so basically the way that you did that was you said 600 millimeters squared plus 250 millimeters squared and took the square root, right? And so you got 650. Okay. And that's exactly right. Okay. Now let's see if we can tie this to what we've done in the past. Remember how we could write a force vector as the magnitude of that force times a unit vector in the direction that we're in the direction of that force. So here's what I'm getting at. I propose if we were to try and draw this frame again and isolating only the forces that we're trying to find out. So in the business, we call this a free body diagram. Oh, free body diagram. So what we mean by free body diagram is, let's take a look at this frame, and here's the frame out in space, and let's see if we can draw all of the forces that are on this frame. Okay, and so first off, we know we've got the reactions here. So Cx. Hold on, let me drop down a bit. Oh goodness, got away from me. All right, so we've got Cx, we've got Cy, and we've got MC. Okay, now just to make sure everybody's paying attention, we also have this force right here, which is, how much is that? 450 newtons. And this dimension is 400 millimeters. And we also have this 750 Newton force. And this dimension is 500 millimeters. And this dimension here is 150. 150. But instead of drawing the cable, what I'm going to do is I'm only going to draw the force that cable exerts on this frame. Okay, and what is that force on this frame? It is a single tension vector right here, right? And what is that tension vector? It's the magnitude times the unit vector. So let's tie this to the stuff that we did in the past, okay? So the magnitude of that vector is 1,300 newtons, okay? Now, how do we get the unit vector? Well, the unit vector is going to be BD divided by the magnitude of BD. So let's express this. All right, so somebody help me out. What is the magnitude of BD? Maybe I'll jump up here a little bit. There we go. 650 millimeters. So this is 650. All right. So 650 millimeters. Now let's see if we can write the vector. Okay. Now this tensile vector goes to the right and then it goes down. Right. It goes in that direction. Okay. So if it goes in that direction, I'm thinking that the x component needs to be positive, but the y component needs to be negative. So somebody write, well, let's take it one step at a time. Somebody write vector BD for me. Remember, this is a vector, so it's going to be IJ format. There we go, 250I and 600J. So there we go. And so what this is going to be is 250 over 650I minus 600 over 650J. And therefore, our tension vector is going to be all of this times our magnitude. And our magnitude is 1300. So we're going to have 1300 newtons times 250 over 650I minus 600 over 650J. So help me out. What's the tensile vector, the tension vector? What does it come out to be? So 500I and 1200J. So that's exactly right. Okay, so everybody with me so far? This should be pretty simple. Okay, what I'm going to do is this. This is how I'm going to do this. I'm going to, first off, I'm going to erase this, not because I'm trying to get rid of it. I just need a little bit of room here. Instead of expressing this tensile vector as just an angular vector, because I like splitting things up into x and y components, I'm going to say that this component here is 500 newtons, and this component right here is 1200 newtons. And that's equivalent, right? That's equivalent as me saying, that's equivalent to me saying just that single tension vector of 1300 newtons in that direction. And in fact, maybe what I ought to do is to ensure that I'm not confusing some of my distances later, is maybe I ought to erase this all together and just put .500 newtons, 1200 newtons. Just so everything's crystal clear. Okay, before I do anything or move on, any questions? Oh, I just realized something. This height here, I think I forgot that. Yeah, and that height is, what is that? 600 millimeters. I forgot to put that on there. Okay. Let me take a sec, make sure everybody's good with this. Everybody good? All right. If you're good with this, then pretty much everything from here on out is going to be pretty easy. Let me move this down a bit just so I can see it a little easier. Wait, just a little easier to see. Okay. So what I'm going to do is I'm going to now apply my equations of equilibrium. And I'm going to apply those equations of equilibrium to solve for my unknowns. What are my unknowns? They're the reactions at C. Okay? So let's just take each one of them one at a time. And that's one of the things that you will find a lot of times when you're dealing with problems with fixed supports is what we did on Monday. We were dealing with hinge roller. We were dealing with simple supports. Sometimes you got to be strategic. You know, like if I sum moments at A, that eliminates two of my unknowns, and then I can solve for the reaction at B or something like that. A lot of times with fixed supports, it's even easier. It really doesn't matter what order that you go in because all the reactions are at the same place anyways. So let's just do it one at a time. So we'll sum forces in the x direction. We'll take all the forces to the right as positive. And we just start going through our free body diagram and one by one writing down all of the forces that we consider. So to make sure everybody's paying attention, do we consider the 750 Newton force? No, that's a vertical force, so we don't consider it. But do we consider the 450? Exactly right. We do consider the 450. So is it positive or negative? There you go. So negative newtons. Okay, what's my next force? Is there any more forces that I know? $500 newtons, and positive or negative? There you go. See, this isn't so hard. This is pretty simple. Okay, now the unknown is CX. Okay, and I have that drawn to the right. Okay, so I'm going to draw this. I'm going to say CX equals 0. Now, that's everything. I didn't forget anything. So, because the other two reactions at C are vertical and moment. They don't matter. And the only other force is at 1200 newtons, and that's vertical. So that's everything. And so let's chug this out a bit. So we've got a negative 450 plus 500 is 50. So 50 newtons plus CX is 0. So if I'm solving this, like an equation, if I have 50 plus x equals 0, x equals minus 50, right? I have to bring it over to the other side of the equation. So therefore, CX is minus 50 newtons. What that means is my assumption was wrong. I drew that arrow going to the right. I'm wrong. It's going to the left. That doesn't mean I need to develop significant emotional distress. Just when I write down my answer, just write, oh, CX is 50 to the left. And that's all there is to it. Pretty straightforward. And then we just keep on chugging with this. So let's do it over here. Let's sum forces in the y direction. Take all of our forces going up as positive. So we just take it one step at a time. So the 750 newtons, we do need to consider that positive or negative. There we go. All right. Give me another force I need to consider. And its sign. Give me another force I need to consider. Negative 1200. Any other forces I need to consider? Positive CY. There you go. Positive. And That's it, right? Every other force is either horizontal or a concentrated couple, so we don't have to worry about that. Okay, so we've got negative 750 and negative 1200, so that's minus 1950. Equals 0. And so now if I bring that on over to the other side, I get CY is positive 1950 newtons. There you go. Now, one thing I'll mention right now, and I actually don't think it's all that necessary. One of the things that your book does is, for problems like this, what your book will do is it'll say, okay, I have a force in the x direction, I have a force in the y direction. Let's determine the resultant. Let's do square root of cx squared plus cy squared to just get a c force, and then, you know, say c is some force at some angle. I don't think that's all that necessary. You can if you want, but I actually, like, because here's the thing. We've got the x component and we've got the y component. Those two values tell you just as much as a magnitude and a direction, because you can, and plus I think you can visualize it a little easier. So I'm perfectly fine with you just leaving the 50 and the 1950, but I'll show you what the book does here in a little bit. Now, I'm going to cheat a little bit, because the last thing I want to do is just scroll like crazy. Give me a sec. I'm going to copy. All right. I don't want to have to keep scrolling up and down, so I just copy and pasted my my image there. Okay, now we need to sum moments, right? We sum forces in the x direction, we sum forces in the y direction. Now we need to sum moments. So we need to sum moments equals 0. And we need to, first off, we need to pick a sign convention. So let's pick that. Now we need to pick a point. Okay, and I want to be crystal clear. It does not matter what point you pick. You can pick any point that you want, and you will still achieve static equilibrium. That's the nice thing about static equilibrium. The static equilibrium doesn't really care where you sum moments about. But that doesn't mean that there aren't points that are strategically more advantageous. When I'm dealing with fixed support problems, typically what I do is I sum moments about the fixed support. I'm going to sum moments about C. This is, for me, I find it easier because at a minimum, I know that two forces just by its definition are going through point C. But you could do other points. In fact, a test to see if you're understanding what's going on is maybe I'll just, I don't know, sum moments about that point. And see if I get the same answer. You will. You'll get a different equation in different terms, but it'll all wash out in the end, and you'll get the same answer. But let's sum moments at C, and let's just see what happens. So let's see. Let's just take each force one at a time. The 750 newtons, does that generate moment at C? Yes or no? So we're summing moments about this point right here, that point right there. And I'm asking, does the 750 newtons generate moment? Okay. I was wondering if my connection was going down. All right. Positive moment or negative moment? Help me out there. There we go. And what is the moment arm? How far is that from C? Remember, moment arm is always the shortest distance. So 500, there we go. Exactly right. Okay, now, how about the 450 newtons? Does that generate moment? And so if you wonder what I'm doing is I'm sort of training you to think about I guess different ways of or not different ways. I guess I want you to think about a systematic process to go through in going through this. So let's help me out. The 450 newtons, does that generate moment? Yes or no? Talking about this force right here. There we go. All right, I'll start calling on people if I have to. Yes. So it does generate moment. It's positive moment. And what's the moment arm? There we go. I'll start calling on people, I promise. Okay, now let's deal with these. Now, I'll go ahead and tell you that yes, they do generate moment. But what is the deal with that moment? Is it positive moment or negative moment? Yeah, they're both negative. Okay, so this, and I'm running out of room here, so I'm just going to sort of write it down here. So it's 500 times a moment arm and minus 1200 times a moment arm. What's the moment arm for the 500 newtons? There you go, 600. And what about the 1200 newtons? What's the moment arm? 150. There we go. All right. Lastly, does the CX or the CY generate moment? No, that's exactly right. They are going directly through C, okay? But MC does, and I have MC drawn in a counterclockwise fashion, so that's positive equals 0. So if you were writing this on notebook paper, you know, I have it like on 3 lines. You would have it as just one big equation. And so maybe let's see if I can clean this up a little bit. Let's see what I can do. All right. 750, let's start chunking some numbers here. 750 times 500 is 375,000. So 375 Newton meters plus 450 times 400. Are your distance arms always positive, or do they change direction? That's a great question. That's a really good question. Mr. Page asks, do the moment arms have a sign? That's a great question. The answer is no. Whenever you are taking moments, don't think of the distances as being positive or negative. They just have a magnitude. What matters is whether or not the moment is positive or negative. So the moment is defined by a magnitude and a direction. The magnitude of that moment is the force times the moment arm. So the sign doesn't really play into the moment arm itself. The only thing that matters when you're summing moments as to whether or not it's positive or negative is, does the moment generate a counterclockwise moment, or does the force generate a counterclockwise moment, or does it generate a clockwise moment? Everything else just goes into the magnitude. And so the signs don't really matter. That's a really good question. Was that a clear answer? Good deal. Thank you. All right, 180,000 Newton meters. That's 450 times 400. Okay, 500 times 600. I think that's 300,000. Yeah. minus 300,000 Newton meters. And then we have, let's see what else, minus 1,200 times 150. Okay, so minus 180. Plus MC equals 0. Okay, so let's see if I can clean that up a bit. So I've got a plus. Oh, you're absolutely right. You're absolutely right. I'm sorry. That's 100% correct. It should be Newton millimeters. See, that one was minus. There we go. Yeah, I think that. Yeah, thank you. Yeah, I'm glad you put that out. Okay, so let's look at the numbers. So the 180 and the 180, that cancels out. Should we convert them to meters when we do these? You don't have to. You can. And there's argument to be made that if the numbers get a little big, that maybe you convert them to meters. That's a good point. You don't have to, but you can. And I'm not going to tell you. Let me respond to that. I don't think that there's a right way or a wrong way with that. You can convert them or not. As long as your final answer that the units match, I'm fine with that. Because the way I look at it is your particular field of analysis will dictate the unit. So for instance, if you're doing civil engineering structural analysis, you're going to be doing a lot of your forces and kips and your distances and feet and whatnot. And so as long as you're using conventional units, it'll all come out in the end. Okay, 180 cancel. 375 minus 300. So I've got 75,000 Newton millimeters plus MC is 0. And so I'm getting that MC is negative. I'm getting that MC is minus 75,000 Newton millimeters, or negative 75 Newton meters. And so you can just divide that by 1,000 if you'd like. And so that came out negative. Okay, so let's summarize our answers. So what did we get for our three values? Oh man, I went too far. So CX was minus 50, CY was positive 1950, and this is negative 75. So CX is 50 newtons, and what really matters is the direction. And because that's negative, that's to the left. CY was 1950 newtons, and we got a positive answer there, so that's upwards. And MC was 75 Newton meters, and we got negative, so negative is clockwise. And there you go. That's it. So, I mean, hopefully that wasn't that bad. You know, I mean, I don't really think it's that hard. I think it's pretty straightforward. Any questions before we call? I'll say one thing. I have a problem on the homework assignment that it's very similar to this. There's maybe a bit more going on with cables, but I really don't think it's all that more challenging. And I think the overall point I want to make is I don't really think that this is very challenging at all. Now, I'll tell you, on Wednesday, we're going to take this and see if we can extend it into 3 dimensions. So what we're going to be doing is a bit more, R cross FE and a lot more IJK terms with the vectors. So it's probably a good idea when we were doing this to kind of introduce this again, the vector notation, simply because we are going to see it again. But yeah, Wednesday we're going to do this in 3 dimensions. I actually don't really have much else for today. I want to let today's lecture kind of sink in. You all have a homework assignment that exercises this. That's pretty much all I have. Unless anybody has any questions, we can go ahead and call it a few minutes early. I'll give everyone a chance to see if you have any questions. All right, I'm letting you off early. I will see you all on Wednesday, and we'll enter the 3rd dimension again. That's all I have. You all have a wonderful day. Stay safe, stay healthy. We'll see you on Wednesday.